All right, so in this video, we're going to learn about vectors, and this takes us into the application of the math we've been learning and applying it into a physics concept. Now, before I get to what a vector is, we need to first talk about what a directed line segment is. A directed line segment is nothing more than a line of a particular length that has some kind of direction. And we know of that as having a line, or in this case, multiple lines that have the same slope. So let's say I have a directed line segment that's a fixed length that goes from start to finish. That's about that long right there. Now, what I can do is say, all right, well, every directed line segment has to account for where it starts and where it finishes. So technically, if I drew a couple of these and just kind of placed them all over the place, every one of these line segments is different because they have different starting and ending points. Well, a vector represents the set of all directed line segments that have the same length and the same direction. So what I could think of it is, if I draw a new set of axes here, vectors don't care where the directed line segments are, so we're going to let this vector representing all four of those line segments be located with a starting point at the origin, so that's my initial point, and its terminal point somewhere over here that looks like it has the same slope, and it has to go from start to finish. So I go from start to finish, and that is my vector. Now, since this vector represents line segments that all have the same length, the length of a vector is its magnitude. And the direction we're going to get to a little bit more in depth in a little bit, but the direction is going to be the angle formed off the right-hand side of the x-axis from the right side of the x-axis going counterclockwise. Now, let's talk about how to find this vector. I guess it's component form per se. So I'm going to draw another coordinate plane here, and so that way it's a little bit bigger. So I have y, I have x, and I'm going to make that vector I draw where I have my initial and my terminal points a little bit more spread out. So initial point, terminal point, we put the tail on it so that way we indicate what way it's going. And so what we do here is you think of a vector and its components by, well, how far, what's the change? What's the change from start to finish along the x and along the y? Now, vectors in component form, so the component form of a vector, I'm going to call this vector v, is nothing more than writing the vector in terms of what was the change in x by the change in y. It almost looks like a coordinate, but it's not representing a coordinate. It's representing change along the horizontal and change vertically. And the magnitude, so the magnitude of a vector, which there's various notations for it. A vertical line around vector v, it's not necessarily the absolute value in context of vectors. Sometimes you'll see double bars. It still means the same thing. Now, if I refer back to this right triangle, the magnitude of vector v is the hypotenuse of that. And so you would use Pythagorean's theorem where I'd go leg squared plus leg squared equals hypotenuse squared. And if I took the square root of that sum, the magnitude of a vector is the change in x squared plus the change in y squared. So that tells me how long the vector is. So it's nothing more than using Pythagorean's theorem. Now, the direction angle is a little bit more complicated because vectors can point in any direction depending on what the signs are for its individual components. And so we have to think about this kind of like what we do around the unit circle. So let's say the vector points in quadrant 1. And so actually, even before I get to that, I'm going to draw a vector, just a generic vector. I'm not going to put it on a coordinate plane. And let's say it goes up and to the right, and here's the right-hand side of what the x-axis would be. Its direction angle would be the angle of rotation off of that in a counterclockwise direction. Call that theta. Well, if we go back to the component form of the vector, so vector v being in component form as change in x by change in y. My change in x here is one leg of the triangle, right triangle that's formed, and the other leg of the right triangle is my change in y. Well, if I look at this and think, all right, well, how would I solve for theta if this was just a right triangle and not tying it into vectors? I would have opposite and adjacent sides, and I'd use tangent. Say tangent of theta is equal to opposite side, which would be my change in y, divided by my adjacent side, change in x. Now, we have to account for the different signs for x and y based on what quadrant it is. And so what we're going to do is we're going to solve for a reference angle, which would be the quadrant 1 version of theta. And it disregards what quadrant it's actually pointing in. We'll just adjust for it later. So the reference angle for theta is going to equal the inverse tangent of the absolute value of the change in y over the change in x. And then we can adjust that as needed. So let's say by quadrant here, I have my different possibilities for where it could be pointed. So I got quadrant 1, where we have positive x, positive y. Quadrant 2, where we have negative x, positive y, in terms of the components. Quadrant 3, negative, negative. Quadrant 4, positive, negative. If the vector lies in quadrant 1, the direction angle is equal to the reference angle, theta. If it lies in quadrant 2, the direction angle is equal to 180 minus the reference angle, so 180 minus theta. If the vector points in quadrant 3, the direction angle is equal to 180 degrees plus theta. And if it goes in quadrant 4, the direction angle is equal to 360 minus theta. So that's how we find the direction angles of vectors. And one last part, it talks about a unit vector. Now, a unit vector has a magnitude of 1. In fact, every single one of them does. A vector has two components, per se. It has both magnitude and it has direction. So if all unit vectors have the exact same magnitude of 1 unit, their sole purpose is to just tell me the direction in which a vector points. So what its direction angle is. The way we would find a unit vector is, let me draw a generic vector. So I got vector v points this way. So here's my vector v. And when it has its components, so it has its change in x and its change in y. And we have its magnitude here. So this be the magnitude of vector v. Now, because all of these unit vectors have a magnitude of 1 unit, I have to scale this vector so that the magnitude is equal to 1, which means that I'm going to multiply all of the sides of this triangle by 1 over the magnitude. or basically just divide by that. Which means that a unit vector, what you do is, you're going to take the components of a vector v. So vector v has components of change in x by change in y. And I'm going to divide those components by the magnitude of v. And that will give me my unit vector. All right, so let's practice a little bit here. And in fact, I noticed I forgot something. We actually have, there's two special types unit vectors. There's the unit vector I. The unit vector I is the vector that goes exactly 1 unit to the right. So it goes 1 unit to the right and that's it. The vector, unit vector j, is the vector that points directly up 1 unit. And we write that because sometimes they will write a vector in terms of the unit vectors I and j. So what I have here is I got 4 examples and how to find magnitude and direction angle for vectors that point in different quadrants. And we'll look here at the very first one on the top right. Let's say I have the vector 12i plus 16j. Now really, that is the vector 12 by 16. Now, graphically, I know this points in quadrant 1. And so what I'm going to have is it's going to go 12 units to the right, and it's going to go 16 units up. And so this vector starts at the origin, and it would go to 12 by 16. And I would draw my line, and then to indicate direction, I'm going to put the tail on it here. And so there's my vector. We want to find the magnitude and the direction angle. Well, the magnitude is basically the length of that line, which, if you don't want to memorize a formula, these vectors make right triangles, where I could do Pythagorean's theorem. Magnitude of a vector would equal the square root of 12 squared plus 16 squared, which would give me my answer there. And so that would be 20. So I have a magnitude of 20. My direction angle here, so we're in quadrant 1. So tangent of theta is going to equal y over x, so 16 over 12. And I would do inverse tangent of that. So inverse tangent of 16 over 12 is going to give me an angle of 53.13 degrees. So there's my direction and my magnitude. Now let's go to a different quadrant. So this vector here, vector v, points in quadrant 2 because it has a negative x component and a positive y component. So I'm going to draw quadrant 2. All right, so there's y, there's x. And so this vector goes to negative 9 on the x, and it goes up to 12 on the y. And so it would start at the origin and then go to that point, and I'd have to put a tail on the end, so that way I see which direction it goes. And we want to find the magnitude. All right, so the magnitude, if you close in that triangle, the magnitude is the hypotenuse. So it equaled the square root of negative 9 squared plus 12 squared. which would give us 15. Now, my direction angle here, see the direction angle is the angle I'd rotate off the x-axis, again the counterclockwise direction. So to find that, we need to first find the angle formed in that vector makes with the x-axis that it's closest to. So we would say tangent of theta is equal to opposite 12 over adjacent -9. Now, I'm going to take the absolute value of that to ignore the sign. So theta is going to equal the inverse tangent of the absolute value of 12 over -9. And that's going to give me this reference angle. Which is 53.13 degrees. Now, that's not my direction angle. Because it's in quadrant 2, my direction is going to equal 180 degrees minus 53.13. So let's take that away from 180, and my actual direction angle is 126.87. So my direction angle and my magnitude. So that's quadrant 2. Let's go to quadrant 3. All right, so I have a vector here written in terms of the unit vectors I and j. That is basically the vector -24, -32. And so graphically, we can draw quadrant 3. This vector is going to go left 24, so we're going to go -24 on the x and all the way down to -32 on the y. And so the vector would be somewhere down here. I'm not drawing the scale. Starts at the origin, points down to that point in quadrant 3, and I got to put the tail on the end of the vector. And we want to find magnitude and direction. Remember, the magnitude is the hypotenuse. So the magnitude is going to equal the square root of -24 squared plus -32 squared. Which is going to give me 40. So that's how long that vector is. The direction angle, my direction, is going to be how far did you rotate counterclockwise off the positive x-axis? Well, in order to find that, I'm going to have to find the angle formed between the x-axis and that vector, call it theta, and I'd add 180 to it. So I look at my components here. You got -32 for this leg, -24 for that leg. So tangent of theta is going to equal opposite over adjacent. And I go solve for theta. So theta is going to equal the inverse tangent of, that makes positive. That just to keep with the notes, let's say the absolute value of -32 over -24. And I would get my reference angle. So inverse tan, 32 over 24, and we got 53.13 again. So that's my reference angle. So quadrant 3, your direction is going to equal 180 degrees plus 53.13. So my actual direction angle is 233 degrees, or 233.13 degrees. So there's a quadrant 3. All right, if the vector was pointed in quadrant 4, so quadrant 4. All right, so this one goes to +10 down to -24. And I want to draw my vector. So there's the ending point, initial point at the origin. I connect those. I put my arrow there to indicate direction. And we want to find the magnitude. So magnitude, think of that as a right triangle. the magnitude of r is the hypotenuse of that triangle, and you got sides of negative 24 and 10. So it'd be the square root of 10 squared plus negative 24 squared, and I get my magnitude. (26). Now the direction angle here is counterclockwise rotation off the positive side of the x-axis. So in order to find that, what we're going to do is we're going to find the angle inside the triangle here first. So tangent of theta is going to equal y over x. So negative 24 over 10. We're going to take the absolute value of that to get this reference angle. So theta is going to equal the inverse tangent of the absolute value of negative 24 over 10. And we get our reference angle here to be 67.38 degrees. Now, our actual direction angle, because it's in quadrant 4, is going to equal 360 minus 67.38. Which means that the direction angle for this vector is actually 292.62 degrees. So direction angle magnitude for all 4 quadrants. One last thing here. Let's say I'm actually given the magnitude and I'm given the direction angle, and I want to write it in component form. So I want to write the vector in component form. Well, to do this, we have to kind of think a little bit about, well, they've already solved for magnitude for me. So I have this vector here, vector n. And I know it's pointed, its angle is 330 degrees, but I'm going to make a general example here. So here's my vector with my magnitude, and I have its direction angle here. And I'm going to come back here to make this right triangle. Now, we know that this is supposed to be the change in x, and this is supposed to be the change in y. Well, if I apply my right triangle trig rules, and I could rewrite change in x if I use the cosine function, where I could say cosine of theta is equal to adjacent over hypotenuse. And if I multiply the magnitude of n over the magnitude of vector n times cosine of the direction angle is equal to the change in x. And if I do the same thing for y, and say, all right, well, y in context of theta and the magnitude, sine of theta is equal to opposite over hypotenuse, which means that the magnitude times sine of the angle is equal to my y component. And so our component form, if we don't actually know the components of the vector, can be written as magnitude times cosine of the angle by magnitude times sine of the angle. All right, so this is actually relatively simple here to get our answer. So all we have to do is type into our calculator, and we get our answer. So our magnitude is 94, and the angle is 330. So I would just say that the x component is 94 times cosine of 330, or the x component is, and the y component would be 94 times sine of 330. I don't have to do anything else other than put that in my calculator. So 94 cosine 330 gives me an x component of 81.41, and the y component is negative 47.